I'm going to give you a brief overview of what JEOL is doing with mass spectrometers. Just very briefly talk about the MALDI and DART systems and really mostly focus on GCMS and Pyrolysis GC-GC-MS. Some of you have seen this presentation before. I know a couple of you we talked to in a group meeting just a while back, but there's some new stuff in here as well. So let me go ahead and get started. Uh, just to remind you what we're working with, we've got three GCMS systems. We've got a single quad, a triple quad, and the reflector on time of flight. I'm mostly going to be talking about the time of flight system, but we'll have some data from the single quad as well. And in addition, we've got the AccuTOF DART ambient ionization toolbox and imaging multi-TOF system, the spiral TOF. Again, just a brief overview of these because that's not really the main focus of this. But the spiral TOF is our multi-TOF system. It's got a really unique set of ion optics, as some of you may know. We've got essentially a 17-meter flight path coiled up in a 1-meter distance using electric sectors to achieve what's called perfect focusing ion optics. So that means that at least ion optically, we've got 100% transmission. Of course, nothing's ever perfect. You can have ion neutral collisions in unimolecular decay, but the ion optic transmission is 100%. That allows us to achieve resolving powers of more than 75,000. We've even gotten up as high as 130,000 if the sample preparation is perfect. And at the 15-meter point, we can put an ion gate and isolate a single isotope out of a cluster for high energy CID. Uh, with that, we've got three modes of operation. Essentially, we've got linear TOF. You can see where my cursor is, just for high mass and unperturbed MALDI. We've got the spiral TOF for high resolution, and then TOF for MSMS. All those can be used in single sample mode or a data-dependent acquisition or for MALDI imaging. Here's again another picture of the ion optics showing you how this is set up. Uh, One of the neat features about this, of course, is that small differences in the sample origin have no effect on the resolution because it's such a tiny fraction of the total flight path. And again, this is just reiterating what I said. Essentially, we've got a linear TOF, a spiral TOF mode with a resolving power of uh, actually more than 80,000 in some cases. The long flight path flattens out the resolving power curve as mass dependence of resolving power from delayed extraction because the delayed extraction region is really short compared to 17 meters. And the monoisotopic precursor selection is really helpful for CID to get, you know, valid MSMS spectra without interferences from adjacent peaks. Uh, then one of the things that I'm not really talking about, but I think it's of interest that we have specialized software functions for polymer imaging. For example, we can image a sample by Kendrick mass defect, or we can image a sample by average molecular weight and image a spectrum by average molecular weight and polydispersity, and that's been really helpful in trying to characterize polymer surfaces. For example, looking at the differences in aging and in homogeneous sample deposition and that sort of thing. We do have an online polymer data book with examples of each of the three different modes for different polymers. So while I'm not going to be talking about this at great depth, there's a link on the bottom to the polymer data book if you'd like to see examples of data uh, from the spiral TOF for a pretty large variety of different kinds of polymers in all three modes. We do have polymer analysis software based on Kendrick mass defect analysis. It's a fairly easy program to use with simple graphics. Does end group analysis, molecular weight distribution, and degree of polymerization plots. We also use the AccuTOF DART. There'll be one example of that in the bulk of the talk. But I've done a lot of work with thermal desorption and pyrolysis with the AccuTOF DART for polymer analysis. We have a variety of inlets on this. I mean, DART is the main one, although we've done paper spray for EO-PO copolymers, both block and random. I've done inlet ionization for a few things and even flame ionization occasionally. Recently, we were looking at inorganic materials and hemp rolling papers, metals that shouldn't be there. But thermal desorption and pyrolysis DART is good. We've also used the plasma and DBDE source, electrospray, APCI, and cold spray. The really major part of this, though, that's relevant is the DART source. And here's a short schematic of the whole thing. The atmospheric pressure interface is here with two off-axis skimmers, a bent RF ion guide, and a reflectron. The atmospheric pressure interface is great because I can put anything in front of it, no matter how dirty, and we never really contaminate the back end of the mass spectrometer. I won't dwell on how DART works. You've probably all seen the Wikipedia diagram, but essentially we're just using heated gas containing electronically excited helium atoms that will ionize the sample by proton transfer or hydride abstraction. What is useful, though, is this thermal desorption and pyrolysis attachment, which allows us to do a temperature program thermal desorption and pyrolysis measurement with the DART, much like the evolved gas analysis that we do with the GCMS systems using the Frontier Lab pyrolyzer. Uh, Thierry Fouquet and Chikako Take and I published an article on this a while back that'll give you some examples of what we're seeing. The data are complementary, I think, to what we see by GCMS. If I put a sample directly in the DART, I can see the additives just really jump out. Whereas with the thermal desorption pyrolysis, additives do show up, but we get better spectra for polyolefins like polypropylene than we would by trying to measure those directly in the DART gas stream. That'll come up in an example of a plastic bag a little later. But the main focus of the talk for me is the Accutop GC Alpha and the MS Fine Analysis software that we're working with. This is our 6th generation GC time of flight system. It has very simple ion optics, really just a dual stage reflectron, a single reflectron. But the resolving power is 30,000, high speed, wide mass range down to mass 4 up to MRZ 6400. You'd think that's irrelevant for GC, but for field desorption, we can see molecular weight distributions for some small polymers. And we can also do GCGC, which will come up in a bit of the talk later. The nice thing about this and all of our GCMS time of flight systems is that we've got all of the available ion sources. We have chemical ionization and electron ionization, of course, but we also have field ionization and photoionization, which allows us to get molecular weight information that would be hard to get otherwise. And none of that would be useful if we couldn't do quick ion source exchanges with fast pump down. And what's really been spectacular for me is the development of the data analysis software that I'll be talking about. For the pyrolysis measurements, I'm using the Frontier Lab multi-shot pyrolyzer. Of course, we support other pyrolyzers that could be mounted on an Agilent GC, including the Gerstel system. For this measurement, though, this is what we're using. Some of you, I'm sure, are familiar with this, but it's a furnace-based system that allow us to do things like evolved gas analysis with a temperature profile or multi-shot measurements, or there's even a cryotrap for trapping, heart cutting different parts of the chromatograph and looking at them with more detail. This is what it looks like in our lab. This is actually the previous system, but we just replaced it with one that looks identical. We've got the Agilent GC on the left. You can see we have a Sepsolve Insight thermal modulator for GCGC. The Frontier Lab pyrolyzer is sitting on the back right now. It was lifted off so we could do something else, and we've got the controls for the pyrolyzer right here. In addition, I've got a temperature control box because we've made a modification that allows us to heat up the transfer line as high as 450 degrees for high temperature samples. Mostly that's been used for high boiling petroleum compounds, but it could come in handy for other things. And you also see a programmable reference inlet and power supply for the photoionization source, which is not installed right now. This gives you an idea what everything looks like in place. We also support different auto samplers. One of the ones I like is the HTA 2800T from HTA in Italy, which does liquids, headspace, and SPME all in one. But for today, really, I'm just mostly talking about data from the Frontier Lab multi-shot pyrolyzer. Lots of data analysis resources. I see David's here, and of course, Sierra has the premier software with their Polymerics and Investigator software. Terifukei's Kendo software, MyMass Mountaineer, and MS Repeat Finder. And in my talk, mostly you're going to see a couple of examples from the Frontier Lab F-Search software and JEOL's MS Fine Analysis software. We have a version for both the quadrupole and the time of flight. Of course, the time of flight data supports accurate mass data, which of course will be really helpful for some of the things I'll show you later. We developed this a few years ago. The first version was for qualitative analysis, and the idea was to combine all the information from EI and soft ionization with the accurate mass data, retention index matching, library search, isotope matching, all of the information that we could get from a GCMS analysis to get higher confidence in the compound assignments by database searching. This whole flow chart works as well for the quadrupole system, but of course only the accurate mass measurements and for both the molecular ions and protonated molecules and things, and also from the fragment ions. For each candidate composition, we'll calculate the composition of the fragments and score a candidate composition by how well all of the fragments can be accounted for by that combination of elements. Version 2, they added variance analysis, and frankly, the retention index matching also came with version 2. And that allowed us to look at differences between batches of samples. I'm not really doing much of that with the talk today, but it allows you to do a statistical analysis to find out what's different between two batches of samples and then try to name the differences by using all of the other available information. And the third version, then they added target compound identification, and we added something that's really been spectacular, and that's an AI library. We, there are probably about 600,000 compounds in NIST and Wiley, and that's a really small number of all possible compounds, of course. So we trained a large AI to predict spectra from structure. And of course, this started back in the 1960s. It was one of the first expert systems with the Stanford heuristic dendrol program, but computer technology has really evolved, and we're able to do this with a high degree of success now. So we applied this to the entire PubChem database of over 100 million structures. And to back this up, we also have a local support AI that predicts the presence and absence of substructures to help provide additional scoring for the predicted structures for things that aren't in the database. So this is essentially the same flowchart you saw a minute ago, but we've added another line down here where we have a huge over 100 million compound library to support and supplement the experimental libraries from NIST and Wiley, and then the substructure prediction program. So I'll show you examples here in a bit. Again, the first time we did this with 100 million structures, we've expanded that, and I'll tell you about that in just a moment. But the support AI uses both fragment masses and neutral losses for predictions. So for this to work, we need to have a candidate elemental composition for the intact molecule, and we get that from the soft ionization data or from the EI spectrum if it's present. Version 2, again, we added several things. One was the target analysis function. I'll show you a brief example of that, I think. But the idea of this is for, target analysis can be done a number of ways. It can be done just by database matching, or it could be done by selected ion monitoring or MSMS. But on a time of flight system, we want to rely on all the information, again, not just database matching and elemental compositions, but also retention index matching, accurate mass coverage, everything else that we're getting in all of the data above to score the compound assignments according to confidence. If everything matches, then of course we're going to color code this as a high degree of confidence. If there are candidates with questionable data, then those are flagged in yellow, and things that don't have matches that don't show up from your target list are left out. So we've got target lists for things like volatile organics, for polymer additives, off flavor compounds, and you can create customized libraries. I made one for whiskey aroma compounds and looked for peated scotches and things like that. We've improved the EI mass spectrum prediction accuracy. I'm not going to talk about that very much, but the algorithm that we use to predict the spectra from structure has been refined, and the scores are much more congruent with what we'd expect from the NIST library. I forgot to mention we did train the AI database using the NIST database, and we withheld 30,000 compounds, I think, for a validation suite. The most recent version then again added retention index prediction, again using the published NIST algorithm. So if we have a nonpolar compound like a DB5 or something like that, then we can predict the retention indices, even for compounds that aren't in the NIST and Wiley databases right now, but are obtained from our PubChem database of 100 million structures. And probably the most exciting thing for this group and for me was that we did in silico pyrolysis of polymers, adding I think it says 5 million here, but they actually came up with 10 million structures. So that adds a lot of things that we don't have standards for to the AI database. And for the metabolomics guys, we did in silico silylation of a lot of metabolites in the database. So we've got about 120 million structures in this now. And of course, they added videos. We're up to just about ready for another release, and I'll give you a preview of what's in that one in just a minute. But let's back up for a second and look at what this looked like when it first came out. We first got the software a few years ago. The initial application was for analysis of impurities in fine chemicals, and I briefly mentioned this at the polymer workshop at the ASMS meeting last year. This is one of the examples I made an application note for using impurities in triphenylphosphine. And the first time we ran this, one of these was a chlorinated impurity that wasn't in the NIST and Wiley databases. It wasn't hard to figure out what it was just from the mass spectrum, but that was done interactively by looking at the data. I went back and reran the data with the newer version, and even though this isn't in the NIST and Wiley databases, this is what I thought the structure was, and this came right up as the top match for our AI database. And look at this window. I'll show you more examples of this later, but this is the structure analysis page. For each compound, we've got a PubChem ID, we've got a SMILES structure that can be copied and pasted into things like the MS interpreter. We've got the predicted and measured libraries. We can calculate this for a variety of adducts or losses, of course. And then there weren't very many candidates for this one, but the top match had the highest cosine match score, and we have predicted presence and absence of substructures over here, with the fragment compositions shown based on both elemental composition and neutral losses. These hits can be annotated. Some things are pretty familiar fragments, obviously the 51 and 77 aromatic fragments, but you can make customized lists to search and label the fragments. This one was fun though. I didn't expect this, and when we got the chromatographic deconvolution software in the second version, this little guy popped up. So triphenylphosphine, you've actually got a tin homolog there. I have no idea how it got there, but that's definitely in the sample. My colleague, Dr. Kirk Jensen, has been looking at compostable and recyclable plastic bags for a project. And we did pyrolysis, GCMS, and thermal desorption DART to try to identify additives and polymer compositions. And we used MS Fine Analysis AI to identify some of the the pyrolysis fragments. So when I first ran this on DART, just because it was set up, we used the thermal desorption pyrolysis attachment. And there are essentially three zones of compounds coming out. And this is similar to what we'd see doing the evolved gas analysis on the pyrolysis GCMS system. The first one is here are the spectra for each of the three, and you can see it's pretty much three distinct regions. The first one's obviously polyethylene oxide or PEG 200. That one's pretty obvious. The second one turns out to be cellulose, and I have a small homemade database of polymers here. So that was readily recognized. The pyrolysis fragments of cellulose are essentially dehydrated monosaccharides. And if you have substituted celluloses, of course, some of these fragments will change. The third one wasn't in my DART database, so we measured that by pyrolysis GCMS, and the F-search result showed that it was polybutylene adipate terephthalate, which is a well-known compostable polymer. It's a random copolymer, as you guys probably know better than I. So the F-search database has a number of replicate measurements for this. When you do the F-search match, you get essentially you're summing all the spectra and doing a spectrum search, but they also will show you a comparison chromatogram that you can match to your measured chromatogram if you follow their same chromatographic conditions. So just for fun, we tried to identify what one of the peaks was. And when we fed this to MS Fine, the library search matches don't make sense. You can see if you look closely enough, the top matches both have chlorine and bromine. Here's one of the structures on the right. And it's obvious from the isotope pattern there's no chlorine or bromine present. So these don't work. Instead, we look at the data. Chemical ionization shows us that the protonated molecule is C11H13O2. So if that's the composition, then we have our integrated analysis tab here. This shows us all the information that we have. And if we carry out the AI analysis, this comes up with the structure of the butynyl benzoate. Uh, it's the top cosine match. It accounts for 12 out of the 35 predicted substructures. The match spectrum is good. And the other thing, of course, we've got is a predicted retention index, which turns out to match very closely to the measured retention index. That was a really nice addition to the program because it filters out a lot of unreasonable structures. There's still some manual assessment of these candidate structures if you have complete unknowns. You really should inspect all of the information here. But having that retention index match really makes it much more reasonable candidates for the structure analysis. You can also do a filter by functional groups. If you know a functional group is present from some other information, then you could filter by aromatic or carbonyl or some other substructures, and that'll give you a smaller list of structures to sort through. What I'll often do is take a candidate structure like this and feed it with the measured mass spectrum back to the NIST-MS interpreter so that I can see if the exact masses for the fragments match nicely with the predicted structure. Again, all of these are just tools, but that and the NIST hybrid search, all of these are really helpful ways to try to look at this sort of thing. So that's what MS Fine Analysis came up with for something that wasn't in the NIST and Wiley libraries. This one happens to be in the Frontier Lab library, and the F-search result matched exactly with what we'd predicted. So this is at least one independent support for the candidate composition that our program came up with. Kirk found a fun result in one of the bags that he bought on the internet. So let's show you what happened with that one. This was supposed to be a compostable and biodegradable plastic bag. Several of them were biodegradable, but this one is inconsistent. The product description says it's made from polylactic acid, but then it has two different comments about which method that it's been tested by. One of them is an anaerobic method, and the other one is an oxidative degradation. Of course, both are inconsistent. So we just ran this on the pyrolyzer and fed it to F-search, and of course, it turns out just to be polyethylene. And looking up this company, they apparently have added some sort of mineral catalyst, which is supposedly helping it break down, but there's some question about whether that's really valuable or not. Anyway, it's polyethylene. It's definitely not polylactic acid. But this does lead to more discussion about polyethylene. We've been interested in pyrolysis of polymers from the point of view of recycling plastics. And this was one of the references I found showing what sort of things happen for a commercial grade pyrolysis of polyethylene. I think that GCGC with a high resolution time of flight is a good way to monitor pyrolysis reactions on a small scale and maybe characterize the products of a pilot plant pyrolysis. I mean, we've measured pyrolysis oils from customers in the past. I can't share any of that with you, of course, but it's a good way to characterize these complex pyrolysis products. And I think having both high-resolution mass spec and soft ionization really helps us to sort through complex chromatograms. If you look at the pyrolysis data book, that's really the basis for the Frontier Lab database. This is the entry for polyethylene. And those of you who work with pyrolysis, of course, this is really familiar. It's going to look just like what we see here. But the chromatogram itself is pretty simple. It's a one-dimensional GCMS measurement. Essentially, you're basically just getting the alkanes, alkenes, and alkadienes as the major peaks here. That triplet goes out in time. Now, this is a fast GC run, so things start to merge at later times. There are a few little peaks in the baseline. But what does this look like if we do this by GCGC? It's a much more complex chromatogram. Here are those triplets you're seeing, but each blob here is a different compound, and there's several things that aren't obvious from the one-dimensional GCMS measurement. If we assign some of these blobs here, you can see some of these things are aromatics, alkyl aromatics and things like that. If we zoom in on this region, there is our triplet, but look at all the other little dots here. All of these blobs are separate compounds. We can zoom in on some of those and try to identify what they are. And we're finding things like cycloalkanes and alkenes, alkadienes and even cycloalkenes showing up. So each of those things is a different compound. It's a much more complex mixture than you would guess just looking at the 1D chromatogram. So what happens if we looked at oxidized low-density polyethylene? We see a much more complex GCGC chromatogram. This is a standard we bought with the Polymer Standards kit. So this has got an acid number of 16 milligrams of KOH per gram. But look at all the extra peaks that pop up between here and here. Some of these are common. Again, the aromatics are still present, but there are a lot more oxidized peaks here. And if we zoom in and look at those, you can see what some of these are. We've got ketones and aldehydes showing up with different degrees of complexity there. There's a zoomed in region showing several of these things. And we also should expect there to be acid present because oxidized polyethylene is characterized by acid number. So the acid peaks weren't really obvious from either chromatogram. If we had done negative CI, we probably would have seen them, but it's an easy way to just look for a chromatogram for a characteristic fragment from the organic acids. And if we do that, we can see the profile where the acid peaks are from C4 up to C16 with the largest distribution for the lower molecular weight acids. So just recently, we've added support for GCGC data to our MS Fine Analysis AI software. And I just received a beta test version of it just this past week. And I went back and looked at the oxidized polyethylene data. This has been really nice. It provides us an ability to align both the EI and soft ionization chromatograms. As you can see here, I've picked a single peak out of the data, and these are aligned both in the X and Y axis. On the bottom, we see the tabular results. The peaks that are highlighted in pale blue are those that have high confidence in the assignment because we have a consistent set of data for EI, soft ionization, retention index matching, accurate mass, and a database search with a high score. If you look at you can pull the data over for each compound as you click on each line, and you can see, of course, we don't really have a significant molecular ion in the EI data, but we do have a protonated molecule in the CI data. And the NIST database match is very good. This is what the integrated data analysis looks like. Again, we've got the tabular summary of all the top hits, EI and CI data, isotope match for the protonated molecule, fragment compositions for each of the fragments, and of course the database information. I haven't really experimented with the AI part of this yet, but those same functions are available. So with GCGC being a really powerful way to look at complex mixtures, sometimes it isn't enough. Kirk was interested in looking at fresh and used pump oil because we wanted to see what happened to the oil itself and also to the additives. And we ran both pump oil samples, and you can see some of the hopanes from the oil must have been from a natural origin because we've got some biomarkers in here. We also see the oh gosh, the diisobutyl phenol additives here. But unfortunately, the oil is what's called a UCM, an unresolved chromatographic mass. There's just too much branching and too much complexity in the profile to really be able to get much detail here. You can infer some things about the degree of branching from the width of this, but it's really hard to get detailed information for individual compounds. And as the polymer ages, the oil ages, you can see what a mess this has turned into. Things have broadened, the molecular weight distribution has shifted, uh, and you can see breakdown products from the additive. Uh, as not everything was identified, but you can see what's happening. Some of these are known degradation products. Some of them were just identified by their mass spectra. But we can get information for this. And if we, again, if we try to do this by looking at the chromatogram, it's almost a hopeless case. But we did field desorption instead and just spotted the oil directly on the field desorption emitter. And in doing that, we get elemental composition information for each of the components. We're not resolving isomers. We have no information about branching, of course, but this spectrum gives us a fingerprint that tells us that it's polydecene. And that alone is helpful information. We've got a molecular weight distribution and essentially a composition for the base oil, as well as the identification of some of the antioxidants. For the oil ages, you can see things have shifted tremendously. Here's the fresh oil and here's the used oil. And if we look at the Kendrick mass defect plots, you can see the fresh oil is primarily 1 degree of unsaturation, one double bond. But the aged oil has multiple sites of unsaturation. We've got 1, 2, 3, 4, even 5 degrees of unsaturation. And the molecular weight distribution has shifted from around 750 to about 450. I've also got little graphs up here showing you, which of these series is the most abundant. You can see 1 degree of unsaturation there, and 1, 2, 3, 4, 5, 6, and 7 for the aged oil. A closer view of this, and for the used oil. And you can also see, of course, some of the things that don't fall along the lines are the additives or degradation products. So out of all this, of course, I didn't talk very much about MALDI-TOF-TOF, but as you all know better than I, MALDI is probably the best way to look at polymer molecular weight distributions by mass spectrometry. Thermal desorption and pyrolysis is fast. If you do this directly in the DART, it's very sensitive to additives. And for DART, contamination is minimal concern if you have a big sample size. I mean, we can essentially stick an O-ring right in the DART gas stream. But what we're missing, of course, is detailed information for each compound for both additives and for pyrolysis products. And with the large AI in silico database now and the structure analysis tools, we have a better chance to at least propose reasonable structures for some of these compounds that aren't currently in the databases. And for more complex mixtures, of course, GCGC high resolution mass spec. I've been going back and looking at some of the data we measured for things like PVC, for example. PVC is going to produce an awful lot of PAHs that are essentially going to have the same retention index in one dimension. So GCGC is a better way to try to get an idea of which isomers are present. And then finally, field desorption, which is no chromatography and no separation of isomers, but a really fast snapshot of the overall composition for for additives and small things like the pump oil. So I think that's what I've got planned for today's talk. So I'll stop and see if there are any questions.
I think Christopher, yeah, go ahead.
Yeah, very excited to ask a lot of questions on those last two studies.
Sure.
Very similar to some things that we are actively participating in. And the first one being on that last presentation, or the last part on the pump oil and the DBE. Did you compare that to iodine values?
No, we didn't. I mean, we're just a mass spec demo lab, so this was an interesting application. Really, I don't know what Kirk was expecting. He may have to leave the meeting early today, but I was expecting to see just the degradation of the additives, but I was also expecting maybe it's some of the materials that got trapped in the pump oil. I guess it was probably from electron microscopes that wouldn't have the level of organics that we would expect from the mass spectrometer. But I guess what's happening to the oil was really interesting.
Yeah,
it's not aromatic. I think these are actually just polyunsaturated.
Yeah, I think so too. And that's what's really interesting to me. And when you compare that against the data from the polypropylene study, is I was going to ask, is there any suggestions you have for a semi-quantitative approach to understand the degree of oxidation? But your DBE part of that presentation does offer at least some potential insights on how to make that quantitatively insightful as well.
Yeah, I mean, as you probably know, most GC people also run flame ionization because it's quantitative, because it's hard to get standards for all the different compound classes. So, I guess at least we have some qualitative way to see what the trend is.
Yeah, and if you can semi-quantitatively translate that DBE value into, you can at least say the degree of oxidation early on. And then finally on that one, have you done it? I know that I've asked already, are you benchmarking against other things? But another factor or analytical technique for looking at degree of oxidative stress is sometimes IR. Did you do any benchmarking on that?
We don't really have it here, unfortunately. We've got electron microscopes and NMR and mass spec, but no IR. But I used to work at Nicolet, so it would have been interesting to see what it looks like.
You would have, I'm just right next door. Yeah. But, okay. Awesome, Chip. Thank you.
Thanks.
Just to add some context to what I was expecting out of the pump oil was that somebody had dropped off that pump oil in our lab, and I noticed that it had only been in use for a short time for what I expect. So pump oils, we typically change out maybe 6 to 8 months is our recommended maintenance period about. And this was like a few weeks. Very odd to pull out this gunky looking sample in just a few weeks. So I was just curious what the difference looked like. And and basically there was just this fast breakdown of the pump oil versus what we might normally expect in a few weeks, I think.
Even just a visible appearance, the used pump oil was darker, and I'm attributing that to all the conjugation and the polyunsaturated materials there.
Thank you.
Yeah,
you got my question.
Very nice work, Chip. When you do GC, the columns are different, I suppose. I mean, or you use the same stationary phase in both columns?
No, actually, GC, I'm sorry, I should have explained for people that don't do GC, but it's the concept's pretty simple. We're using what's called a normal column set, which means we've got a 30-meter nonpolar, essentially DB5 column, followed by a 1 or 2 meter short polarity column. And at the point where the two columns are joined, you have a thermal modulator. So there's a hot and cold gas jet, and every few seconds you trap what's coming off of column 1 and introduce it onto column 2 with a pulse from the hot jet. And then the software knows the modulation period, and it can demultiplex the data into 2 dimensions. There are other kinds of modulators. There are flow modulators. We were using the SEPSolve modulator for years, but we've recently started using we were using the ZOX for years. We recently switched to SEPSolve because they provide software control for flow and temperature during the GC run. We've been using multiple varieties of software. I was using GC Image for the structures you see. SpectralWorks UK makes Analyzer Pro XD, which is really versatile, especially for looking at multiple sample comparisons. And then, of course, our own software has got the features for identifying unknown compounds and identifying known compounds with higher confidence.
Yeah, it's amazing, though, that the acids, you saw acids, so I would expect the acids to stick on the columns, but you did see carboxylic acids, especially the small.
Yeah, that's actually one of the
ones.
benefits of GCGC. We did a paper on earwax, believe it or not, which has all kinds of things, including triglycerides. And because you have both polar and nonpolar separation, you can actually get a much better characterization. Things like cocoa butter equivalents, you usually do those on a specialized 1D column, but GCGC is a really interesting way to try to characterize these things. Another nice thing about it, some people actually propose it as a kind of a complement to FTIR, because the compound classes group in different regions on the 2D chromatogram. And so the location on the chromatogram might tell you something about what functional groups are present.
Nice.
If anybody else has any other questions, I'll do my best to try to answer them.
So the degree of oxidation that you see it's a nice way to classify aging, it seems. I mean, the more aged something is, the more oxidized you'll find them. Yeah. Since we have, yeah, that's nice. I mean, this is, to me, it seems something similar to, I mean, Savannah is here in the audience, but part of her dissertation was to analyze particular sediment in motor vehicle engines. And actually there also, I think she observed oxidized polyethylene. I remember, didn't you see?
Oh, that's interesting.
Yes, oxidized, and that leads then obviously to aggregation, because it becomes polar now and can form those particles. So I thought, I mean, I should give you credit for that. That you did it 5 years ago, Savannah.
We did a study with General Motors for engine oil
degradation.
Exactly.
Hers was also actually with Dow or General Motors, I think. Yeah.
Yeah. Chris, is that published or? Is that published, or should I just send
it's published. It's published.
Okay.
That work is published in Energy and Fuels, I think. Isn't that Savannah? I don't know. You know.
Okay.
Yeah, probably was what,
2020
or so?
No.
Yeah, no, you're right. Probably 2020.
After your dissertation, I'm slow.
Okay.
after you graduate.
Fair enough. Yeah.
Oh, sorry, I muted myself. I had a quick question. This could be an easy one, actually. So earlier in the talk, when you were showcasing the software, I think it was around slide 36.
I could go back to
when you were like, yeah, sure.
Sure. Let's see. Here?
Yeah.
Or...
I think it was a bit before. It was when you were like identifying basically copolyester fragments or pyrolysis products.
Yeah, that would have been.
Yeah.
Oh, okay. This was not this one, but let's see. This one, I think.
Yeah.
This was. Yeah.
So basically, I was curious, like the hits when it was showing when you with the. I think it was like with the terephthalate and butanediol and adipic acid comprised copolyester. So when you were seeing those hits, it's based on the EI fragments, right? And you said that it's like a custom database that you use, or is it already now built into the software that it can identify, polymeric, oligomers?
Yeah, let me explain a little better. I mean, of course, the initial assignment. We're doing all of these things. I guess I don't know what the actual sequence is, but for any assignment that we make on, let me see if I can find one of those tables for you. Let's see, like try to find the starting tab here. Having a yeah.
Maybe it was much more earlier.
It must be. Oh, probably when I was looking at the where is it? I don't think yeah, something like this. This was the early version. Let me see if I can blow that up a little bit so you can see it better. This is the main tab. It's the summary of all of the compounds identified, and of course, this one was easy. Everything was identified with high confidence, so they're all color-coded in blue. But for each of these, we have an EI database match. We have an elemental composition based either on a molecular ion from soft ionization or in the EI spectra, or a protonated molecule. We have fragment coverage, retention index matching. Can't think of what else, but for this, all of those things are consistent. For each of these, there are a number of hits from the database, but only those that are within the constraints are flagged and put in the table. If you want to, and I've pulled over the side window, you can see over here with the detailed information for this compound. This one actually did turn out to be in one of the databases. But if you double click on each of those lines, then you get all of the other tabs that you can examine in detail. And I have to admit, I go through and check these interactively. If I'll check to see whether I agree with the assignment of the molecular ion, for example, or if I'm in CI, whether it's chosen an adduct or a protonated molecule, or which peak it's assigning as the protonated molecule. But most cases, the automation is pretty good. For 1D GC, it takes only a few minutes to do the analysis. I'll usually stop and proofread the peak detection and deconvolution first, though, to see if I think the parameters are catching all the peaks of interest. And so I'll have it halt after peak detection, inspect it, redo the peak detection if necessary, then I'll let it proceed with the analysis. For things that aren't in the database, then this will prioritize database data, that experimental data. But for things that aren't in the database, then if you have an elemental composition, it will go ahead and carry out the AI data analysis. Does that answer the question?
Yeah, as a kind of like a quick follow-up on that, does it also start predicting structures? I think it was right when you were showing, like if it gets like a formula.
It does.
Even if it's not in the database.
Yeah, and that's where we are. Let me make this smaller again. So what you're seeing here is it's the the structure analysis page. So you are going to get a set of structures. Again, you really need to proofread those. We've got 3 scores. One's the cosine match score against the calculated spectrum. One is the number of substructures predicted and present and absent in the structure based on the fragments and the neutral losses. And a third one is a weighted score. It says PROB, but it's not a probability because it has negative scores. It's really just a weighted score, giving some structures more value than others. So, the library database is a local 60 gigabyte database that sits on the local computer, and then the other local AI here tries to predict presence and absence of structures. Honestly, I'll use all the tools available. I use the NIST-MS interpreter. I use the NIST hybrid search. I have a copy of the Wiley know-it-all software, which I think in some ways is similar to the NIST hybrid search. But it will integrate data from FTIR or NMR. Again, I don't have a lot of experience with that, but I do use the NIST tools quite a bit just to confirm it. If I have a candidate structure like this, I'll go back and feed it to the NIST MS interpreter and see if it looks consistent.
If I had 2 questions on the retention indexing, I guess, is
Sure.
that, first off, is that based off, it does some assumptions based off of the column inputs, like if you're using a DB5 versus a polar column, I assume?
Yeah, essentially, if we're doing data from the NIST or Wiley databases, we can specify whether you have a polar or non-polar column. And if that data is in the NIST or Wiley databases, then we're essentially just filtering the outputs or flagging them if we fall outside of a specified retention index tolerance. The tolerance is much wider for calculated retention indices, although when I've compared things that we have reason to believe are correct, we're using the NIST algorithm for predicting.
Okay, so then temperature gets factored into that too, then I guess.
Yeah, I presume so. The NIST algorithm is published. I didn't really look at it very closely, but that is limited to non-polar columns. There's no calculation for polar columns, so we're relying on experimental data in that case.
And then does it do any binning and aligning based off of known compounds in your spectrum as well, or?
You can. The automatic alignment's pretty good, but I have had cases where I've gone back and remeasured something and we'd snipped off some guard column or something like that. And in that case, you have an option to do an interactive chromatographic alignment. So you can specify, you know, this column is in your soft ionization. I mean, this peak is in your soft ionization spectrum that matches this peak in your EI spectra, and you can do that for several data points to align the chromatogram. We're also doing that in the GCGC data, and I haven't fully. I know that when I open that up, there's an option to interactively align the x-axis, but I haven't had to do that for my data.
I think we'll follow up with some more questions on that later on. Then
Sure.
That sounds excellent. Yeah. Thank you.
Oh, you're welcome. Any other questions? Sounds like a no.
Yeah, we still
I
have
don't
3
see
more
anything in
minutes.
chat.
Yeah, I don't see anyone either. But
I've got some new stuff in the works, but that'll show up in my ASMS talk. I was hoping Thierry would join because I wanted his opinion on something, but I haven't heard from him
That was my
lately.
final question is where's theory? So
Yeah.
Hi,
I
this
know
is
he's
Dayan.
aware of it, but
Hello, can you hear me?
yeah, go ahead.
Yeah, just one quick question. Very, very nice talk. I learned a lot.
Thank you.
And the mass spec repeat finder, is that
Yes.
a software only applied for JEOL data, or it can be work for other data from other vendor instruments?
It can. I mean, originally when they introduced it, they were limiting it to JEOL systems, but they've opened it up. In fact, I think Chris has a copy.
Yeah, it's
and,
open to any type of instrument data.
Yeah, I've just imported text spectra, XY pairs, for example.
Yeah, you just need a mass list. So it's just like essentially a CSV file. So
Yes,
with,
yes.
with masses and intensities, and then you can use the software.
That's fantastic.
Yeah, so not as full featured as something like Polymeric or anything like that, but it is a good graphic, simple user interface.
Sure. That sounds great. So give it a try then. Thank you.
Sure.
Well, appreciate everybody joining us. I look forward to seeing some of you in person in Baltimore, I hope.
I'll be there.
Yeah.
Me as well.
Yep.
Yeah, good to see everybody.
Yeah, great to see everyone too.
Yeah.
Yeah.
Thank you so
Good luck
much.
with ASMS abstracts. You know, they're all due
Yeah,
in a
we'll
couple
be there.
weeks.
Got mine in yesterday. Yeah. Thanks, Dylan.
Yeah, no problem.
Steve.
Thank you for
Appreciate it.
giving this
Yeah.
presentation. Yeah. I hope we'll get more of these throughout the year. So feel free to reach out to me or Tony if you want to, present to the group, and we'll set it up.
Sounds
Yeah,
good.
very well done, Selim and Brian and Chief. That's nice.
Thanks, Chris.
Thanks, Chris.
Thanks,
Appreciate it.
everybody.
Thank you.
Yeah.
Thank you.